Swayam Prabha. Digital India. Educated India.
Okay, we'll continue with the discussion on material balance on a co-current mass transfer operation. So we derive this material balance in terms of mole ratio units, and we saw this so here the x1 and y1, these are the mole ratios. At the entry of the equipment, where x and y are the mole fractions or mole ratios at a given location in the operating equipment. And we also discussed that this is a equation of a straight line. With minus Rs by Es as the slope. Now what I would like to do is I want to show this material balance line in the along with the equilibrium line and driving force line. So instead of plotting in mole fractions, let us plot these figures in mole ratio units. Okay, you can see this is a capital Y and capital X. These are all mole ratios, and this is your equilibrium line. This equilibrium line should be given as y as a function of x. Usually we give y as a function of small x, small y and small x, but we have to convert this into mole ratios. Okay, so generally the equilibrium line is given in terms of mole fraction units. You need to convert that into mole ratio units. When you do this, you will see that even a linear line y is equal to mx, a linear line in the mole fraction units will become a curve when you translate into mole ratio units. So that's why I have drawn this blue as a curve, not as a line. And that's very easy to see. You can actually replace this y in terms of capital Y, x small x into as a function of capital X, and then you'll see that it's a non-linear, it's basically a curve, not a line anymore, not a straight line anymore. So the operation we discussed is a transport of A, solute A transferring from R to E. Okay, so our material balance was carried out for this particular case. So now if I were to draw this particular material balance equation, you can locate the point. So this would be x1 and this would be y1. This is the inlet point in the mass transfer equipment. So you can see this the inlet composition is given by this x1 and y1, and that point can be denoted here as a starting point. whereas the outlet composition is the x2 and y2 that can be located somewhere here. This is y2 and this is x2. And I can draw a line with a slope of minus rs by es. So we call this as point P, this is as point Q. Now, so we have, this is an equilibrium line, this is equilibrium line, and this particular line is the operating line or material balance line. So now we also want to see in this particular figure, where do the driving force lines lie? Okay, so for any location on this particular material balance line, suppose if we take point P, corresponding to that bulk concentrations, there will be an equilibrium concentration corresponding to this. Okay, so that point may be pointed out somewhere here, and I can draw a line, and this line would be the driving force line. And this slope is given by minus kx by ky, which is controlled by the rate of local mass transfer coefficients kx and ky. Okay, and if I move to this particular point P, that's the outlet concentration. Corresponding to this, there will be another equilibrium line somewhere here, and this is a corresponding driving force. So you can see this, you start from here at the entry point. The driving force between the bulk concentration and the equilibrium concentrations are quite large. Okay, and then when you move inside this mass transfer operations along this way, you are basically traveling in terms of composition along this red line. At each point on the red line, there is a corresponding equilibrium composition corresponding to this blue line, and the difference between this point and this point is a driving force corresponding to that particular location. So when you enter in the co-current flow, at the beginning there is a larger driving force for mass transfer. As you go slowly inside, the driving force basically diminishes. When you come outside, this is the exit point, the driving force here would have been something here. Okay, so that's a characteristic of a co-current flow and the corresponding mass transfer. Now here, this I have drawn driving force line as a straight line, but actually this will not be a straight line also. This will be slightly curved, because it was a straight line if you use mole fraction units, but the moment you convert into mole ratio units, this will also become a little curved. Okay, the way you can see that is, you can write the equation for the driving force line in terms of mole fractions. So you would write something like y minus yai over x minus xai is equal to minus kx by ky. So this is the driving force line in mole fraction units. So this would be a straight equation of a straight line, provided that you are using mole fraction units. But now if you convert this into mole ratio, so this y can be written as, yeah, so let's see that you have capital Y defined as y by 1 minus y. So from here you can see that so let's see, this is 1 by y. Yeah, so you'll have small y replaced with capital Y by this relation. So this equation then will become So now if you plot this particular equation in terms of capital Y and capital X, this driving force line I was talking about here would be slightly curved. Okay, so but for the pictorial representation I have shown this as a straight line, but this will not be exactly straight line. It will have a slightly changing slope. Okay, but still that will be dependent on the ratios of Kx and Ky. So sometimes what happens is that this is the this is the outlet concentration I mentioned. But suppose if this size of this mass transfer equipment is very large, okay, let's say you keep extending the length of this mass transfer equipment. So what might happen is you can actually slowly go towards the equilibrium line. Okay, so that means if you have an infinitely long material mass transfer operation, the exit composition might reach the equilibrium composition also. So we will call this point as T. Okay, so because of the finite size of the mass transfer equipment, you might somewhere end up here, but then if you keep extending the size of the equipment, you can in principle go to this equilibrium line. Okay, so as you can see, when you go from Q to T, you can also see how the driving force is diminishing as you go closer and closer. Okay, because the driving force becomes smaller and smaller, the mass transfer rate will become very, very slow, even if you extend the mass transfer operating length beyond. Okay, so that's why it takes very long equipment size to reach the equilibrium concentration at the outlet. So, but most of the times this outlet concentration will not be at equilibrium because of the finite size of the mass transfer equipment. Okay. So now this entire analysis is based on the R to E transfer. Now if you do E to R, from phase E to phase R, the entire operation will be just the other side of the curve. Okay, so let me also draw that scenario. So solute transferring from E to R. Okay, this is just a reverse operation. So in this case, you will see again we are using mole ratio units Y and X. This is the equilibrium line. So now the inlet point would be somewhere here. This is Y1 and this is X1. So this would be the beginning point P. And the material balance line will be exactly same as before with the same slope, because the slope is not changed, because RS, so this slope is same as before, minus RS by ES. Earlier we had this line somewhere here. Okay, it's the same line going across the equilibrium line. Okay, so this point is Q, and then if I extend this, I can go to T. So each point here on this operating line tells you about the composition of the bulk phases as you move from the entry to the exit of the mass transfer equipment. And then you can also see that the driving force also will keep changing as you go from P to Q in a diminishing way. Okay, so you can have something like, if I have to draw the driving force line for point P, you might have the driving force line here, and then as you move to somewhere here, the driving force line decreases, and then when you come here, maybe you have a very little. These are all the equilibrium compositions corresponding to those bulk compositions. Okay, this line will be again proportional to this mass transfer coefficients kx by ky. So, so in summary, so if I have to summarize the co-current scenario, co-current material balance, one thing to note is in the mole ratio units, the operating line is a straight line. With a slope of minus RS by ES. Whereas the equilibrium line in X and Y units will be a curve. also the driving force line in xy units will also be a curve. So even if you have a straight line like this in the mole ratio units, when you convert into y as a function of x, this will not be a straight line anymore. Okay, so these are the points to be made as important, because in a given problem, some information may be given in mole ratio units, some information may be given mole fraction units, and you have to work with this same set of units if you want to do any graphical analysis of this problem. Okay, so that's why I'm trying to emphasize using mole ratio units or mole fraction units. You can ask, when can I use this interchangeably? Is there a scenario where I don't have to worry about mole ratio or mole fraction units? Yes, it does. If the compositions are very dilute. Okay, for example, if y or x are in the order of 0.001, that's like 0.1% or below, then whether you use mole ratio or mole fraction, the equation will not change much because the compositions are very less. Okay, so whenever you see a problem where the concentrations are less than 0.1% and you don't have to worry about which unit to use, you can go ahead with mole fraction or mole ratio. Okay, so this is something you have to keep in mind. So now we will move to countercurrent operations and do the same thing. And so some of the conclusions we made about cocurrent may not be valid for countercurrent. We'll have a new set of equations, new set of information that is possible. Okay, so that's why we have to deal this cocurrent and countercurrent differently, okay, or separately in this case. So we have countercurrent operation. So this is the mass transfer operation unit. So you can see this in this particular countercurrent. You can see that on one side, one stream is entering. On the other side, the other stream is entering. So this is the inlet for the E phase, and this is the outlet for the E phase. Whereas in the case of R phase, it enters in the other side and then leaves. So basically, they cross each other in terms of flow. Okay. So this is what we call as a countercurrent operation. This is very similar to countercurrent operation in heat transfer also. Okay, where the two fluids, hot and cold fluid, will enter in the opposite either end of the heat exchanger. In the same way here, in the mass transfer equipment, the two phases are entering in the opposite. Even though they enter in opposite direction, the way we have denoted the notation here is that on the left hand side, we use the suffix 1 for both streams. On the right hand side, we use as with the suffix 2, okay, to denote that the other side of the equipment. So now we can again, the definition of E1, ES, Y1, Y1 the same as what we did for cocurrent flow. The meaning of the notations are still the same. So now we will write the mass balance or material balance. So in the left hand, so you can see that what is entering here is R1, X1, that is entering this, and the other material that is entering here is E2, Y2. Okay, I am doing this operation over an envelope of the. Let me also draw this. Okay, so this is the control control volume that I'm writing the mass balance for. And this must be equal to whatever the stream that is leaving, that is R2X2 plus E1 Y1. So now all this R1, E2, R2, E1, all of them we will write in terms of the solute free molar flow rate, that is the solvent flow rate. So this becomes Rs x1 by 1 minus x1 plus Es y2 by 1 minus y2 Now introducing the mole ratio units, this becomes Rs x1, capital X1 plus Es y2 Rs x2 plus Es y1. Here let us say that you are thinking about transfer from E to S, E to R. Since in the co-current I did for R to E, in the counter current I am doing it for E to R. Okay, but you should be able to do for R to E also. So when we do the counter current mass balance, you also get a straight line for the mass balance, but you get a positive slope. In the case of co-current, we saw a negative slope. In the case of counter current, you will see a positive slope. Okay, so let us draw this line. So the point P denoting this x1 y1 is basically this side, okay, left hand side, and then the other point Q is represented by y2 and x2, that is this, and this line is supposed to have a slope of positive slope of Rs by Es. Okay, so even though the operating lines are straight line for co-current and countercurrent, but the slopes are different. Okay, in one case the co-current it has a negative slope, but the countercurrent it has a positive slope. Okay, and like before, we can also draw the driving force lines. The driving force line for this particular point P would be this. Okay, and then if you go to a point somewhere inside, you will see this is the driving force. So you can see the characteristic difference of the countercurrent co-current flow. In the case of co-current flow, we saw that the driving force was larger at the beginning, and then as you go inside the mass transfer equipment, the driving force was diminishing. Okay, whereas in the countercurrent, you can see that on an average, the driving force seems to be pretty much constant throughout the mass transfer equipment. So by changing the flow conditions, going from co-current to countercurrent, you are able to manipulate the available driving force for mass transfer. Okay, so that's why more often we actually operate mass transfer equipment in countercurrent operations for this reason, that mass transfer rates will be almost equal at all parts of the equipment in the case of countercurrent. In the co-current, the mass transfer rate will be very large in the beginning, and as you go down, it may diminish. Suppose if you have a heat associated with the mass transfer operations, okay, so having countercurrent is better, because as the mass transfer rates are very uniform across the equipment, maybe the heat generated or heat absorbed will be also uniform. So managing heat is easy. Whereas when you do co-current, at the beginning, if the mass transfer rates are high, the heat evolution absorption can be quite high in one part of the equipment, whereas in the other part of the equipment, mass transfer rates are slower and the heat balance will also be different. So you have to have a strategy where the heat removal or supply should be more on one side of the equipment than the other. So you have to think about a thermal strategy to manage effectively. Whereas in the countercurrent, that is not the case. You are able to maintain the mass transfer rates almost the same across the mass transfer equipment. So that's one advantage you can think about. Okay. So as I said, this is for, again, this is the driving force line, and these slopes, the driving force line does not change though. Okay, whether you do co-current or countercurrent, the driving force lines are always negative in this diagram, minus kx by ky. Okay, but only the slope of the operating line might change depending upon the flow conditions. Okay, so again, like I said before, equilibrium line you can't do much because it is fixed by the thermodynamics, temperature, the solute, chemical composition of the solute, which carrier gas, chemistry is involved, temperature is involved, pressure is involved. Once you fix those conditions, equilibrium line is fixed. You can't do anything about it. But in terms of operating line, you have a control. You can change the flow condition, you can change the flow rates, you can change the slope of the operating line, you can have a negative slope or positive slope. Similarly, if you come to the driving force line, there you have a little bit of a control in changing the local mass transfer coefficient by dealing with different kinds of flow conditions. Right? So as a chemical engineer, these are the options we have. How we can manipulate the equilibrium line, operating line and driving force line. Now, why I am emphasizing all this thing, because when we go to different mass transfer operations, the fundamental aspect would be all these, dealing with these three different lines: equilibrium line, operating line, driving force line. Okay, all the design principle will involve working with these three lines, whether it is absorption or distillation or drying or leaching, whatever it is. Okay, regardless of the type of the mass transfer operation, the design basically involves manipulating these three information. Okay, so that's what this is very important, and I'm giving this without giving any particular mass transfer operation specifically. This is general for all mass transfer operations. Okay, when I go to distillation, the equilibrium line will be different function. When I go to absorption, the equilibrium line will be, so mathematical function will be different, but its role in controlling the mass transfer will still be the same. you will be able to write mass balance for distillation, absorption, drying everywhere, okay, but still you have to see the departure from the equilibrium line and operating line as a driving force. So that is going to be the stimulus. So in every mass transfer operation, it will be equilibrium controlled, there will be a driving force line and there will be an operating line, okay. So how we are going to manipulate and how we use them for design is the fundamental question that we are going to answer, okay. So now this is basically for as I said before, we are looking at E to R transport. And you can have this for the opposite side also. This is for R to E. So the operating line lies below the equilibrium line with the same slope of RS ES. The only thing to note between these two is you can see the X1 Y1 is in the other side of the, it's in the higher composition side, whereas in the case of E to R, the X1 Y1 were at the lower composition side. What it means is, if I think about this is like top and bottom, if I have to say this is top and bottom, in the curve here, this is actually top and this is bottom, and here would be just opposite. So this would mean top and this would mean bottom. Because the point P is here and the point Q is here. Like before, we can have a driving force line for each composition here. Okay, so these are all driving force lines. So to summarize, in the countercurrent operation, operating line is a straight line with a slope RS by ES. Magnitude is the same, but the sign is changed from countercurrent to co-current. Second, driving force is almost constant throughout the equipment. The equilibrium line and driving force line will be a curve because of the mole ratio units. The statement that if the mole fractions are less than 0.1%, you can use interchangeably the mole fraction mole ratio units also applies for here also. Okay, that's very general here. But only thing to note here is the slopes are positive in the case of countercurrent and negative in the case of co-current. So whatever I'm talking about co-current, countercurrent differentiation, it is exactly the same as you do for heat transfer. Okay, only thing in heat transfer, we don't represent the equilibrium line and operating line, everything. Okay, we only draw the we draw only the temperature profile. Okay, so for example, in co-current, in heat transfer, you would do something like this. So one fluid is increasing its temperature, other fluid is decreasing its temperature. This is co-current, right? This is TH1, this is TH2, this is TC1, and this is TC2. So here you can see the driving force, which is delta T, is diminishing as you go from the inlet to the exit of the heat exchanger. In the case of countercurrent, so from 0 to x equal to 0 to L, you will see that TC1, TC2, and this would be TH1, and this is TH2, where this delta T is almost kind of constant. Okay, so the heat transfer rate will be almost uniform across the heat exchanger. So we are talking about very similar here, right? In fact, I mean, if you are interested, you can actually even draw these plots for heat exchangers also. Okay, so imagine, so in mass transfer we have this y and x to denote the composition of the solute in two phases. You can think about like something like TH and TC as two coordinates, the temperature of the hot fluid and cold fluid. Where will be the equilibrium line for heat transfer? Y is equal to x, because at the interface they have to be in thermal equilibrium. So you don't have a choice. No matter what you do, TH will be equal to TCI. Okay, so maybe I'll change the color so that we have similarity here. Okay, so this is your equilibrium line with the slope equal to 1. So now we have to think about material balance. Okay, so in the case of so material balance also will give you something like suppose if I do here, for this case, what will be the material balance? I'll have mH, this is the mass flow rate of the hot fluid, its heat capacity, and its temperature TH1, plus mc Cpc TC1 must be equal to, mass flow rate is not changing, heat capacity is also not changing, but the temperature might change. I mean, if you want to keep it simple, maybe you can see the heat capacities are, let's say, same, so you can easily take them out. So you have, suppose if you say Cpc equal to Cph, it becomes much more easier to see the connection here. So you can see this is also an equation of a line between 2 points. So you'll see a line something like this. The slope will be given by mc by mh, and oh sorry, this is actually co-current, right? So it will be like this. All right, so this is my TH1, TC1. So this will have a slope of minus mc by mh, and this would be your TH2 and TH1, sorry, TC2. So you can show here also that similarly you can do for countercurrent also. There is a equilibrium line which is also fixed. For countercurrent, you will see also this is a line with a positive slope of mc by mh. So you can do exact. So generally in heat transfer we don't do this way. Okay, we just get the LMTD and then we go ahead with the calculation of heat transfer. But now since we are doing this in mass transfer operation, putting the equilibrium line, operating line, and driving force line, you can also cast the heat transfer problem the same way. Okay, even though it is not dealt this way in heat transfer. Okay, all right. So that's all for today. I'll stop here and I'll meet you tomorrow.